difference equation is an equation of the form a times un plus 2 plus b times un plus 1 plus cun equals 0, where un is a sequence. A sequence is a function of the natural numbers. The domain of a sequence are the integers, are the positive integers, 1, 2, 3, 4, etc. So u1 would be the first term, u2 would be the second term, u3 is the third term, and so on. Un is the nth term. The term after un would be un plus 1, and the term after this would be, we just add 1 onto the subscript, and we get n plus 1, or un plus 2. Now the solution of this difference equation has this form here. P and Q are some numbers. Alpha and beta happen to be roots of a characteristic equation associated with this. Now I'll explain more about that later. I want to show how this is a solution. What are the consequences of this being a solution by plugging it into this difference equation, setting it equal to 0. So to plug it into this, we have un. We're assuming that this is a solution. We need un plus 1. We get un plus 1 from un. Basically, we just replace n with n plus 1. And that we'll plug that in for this. And we also need un plus 2. So we just look at this and replace n with n plus 2. So now I'm going to write this out with these replacements. So we're going to have a is some number, times un plus 2, which is times this here, plus b times un plus 1, which is this here, plus c times un, which is p alpha to the n plus q beta to the n, and I'm going to set this equal to 0. So we're assuming a solution of this form here, and from that we can learn something about what numbers alpha and beta actually are. So what I'm going to do is factorize out alpha to the power of n. I'm going to factorize that out of here, here, and here. That's where it appears. So if I factorize alpha to the power of n out, what am I left with? Well, I'm going to be left with a times p, and I'm going to be left with alpha squared. Now you can check this yourself. If we multiply alpha to the power of n by alpha squared, we just add the powers n plus 2, and we get this term here, which is what we want. We also want to get this term, so we'd have to write down bp times alpha to the power of 1. Because if you multiply alpha to the n by alpha to the power of 1, we get alpha to the power of n plus 1. Okay, so we will get this term. And finally we want to get this term, so we just put cp here. We just have alpha to the n times cp, giving us this term. Now we also factorize out beta to the power of n. So this will follow a similar pattern. We have a times q times beta squared in order to get this term back. Don't forget the a times it. And then we have b times this term here, b times q times beta. We want beta to the power of 1 now, because beta to the n by beta to the power of 1 gives us beta to the power of n plus 1. And finally we want to get this term. Well, we just have c times q here, and we're setting all of this equal to 0. Now we want all of this thing here to be true for natural numbers, all the positive integers. Okay, so we want all of this expression to work out to be equal to 0. Now the only way we can ensure that happens for all values of n is the variable. So what I'm highlighting here is the part of this expression that varies. A, P, alpha, and Q are constants. I've just written down all the constants here. That is fixed numbers. Okay, they don't change. So the only way to ensure that all of this expression is 0 is if the coefficients of our variable terms, In other words, if all of this here and all of this here is really, you can think of it as the coefficient of this term, which is variable. Okay, we're taking all values of n equals 1, 2, 3, 4, and so on. Everything has to equal 0. So this thing here is identically 0, everything in here. Then it doesn't matter what n is. The whole lot will be 0. We'll have 0 times alpha to the power of n, which is 0. And to ensure we end up with 0 on the right hand side, we want all of this expression here to be 0 as well. So what we'd have then is alpha to the power of n times 0 plus beta to the power of n times 0. Well, that's definitely 0. So it doesn't matter what n is. N, remember, is an integer, and it varies. So what we have to do is set these expressions here that I've highlighted here in this color to 0. So I'm just writing them up here. I'm just writing this expression here up here, and this expression here, I'm writing it up here. We want them to be 0. So we can divide across by p here, assuming that p is not 0. Let's assume that p is not 0. Remember, we're assuming a solution of this form here. This is the solution to our difference equation. Well, p could be equal to 0 actually, but we're assuming here that p and q are not equal to 0. P is not equal to 0. Q is not equal to 0 for now. That enables me to divide across this equation by p. So if we divide all of this by p, we get a alpha squared plus b alpha plus c equals 0. And since q is not equal to 0, dividing this by q, we get a beta squared plus b times beta plus c equals 0. So what you can see now is that alpha is a solution. Alpha and beta, actually, alpha and beta are solutions of what's called a characteristic equation. The characteristic equation is got from our difference equation. We replace un plus 2 with x squared, replace un plus 1 with x, and we just leave off the un here. Alright, see, if you plug alpha in for x, we're going to get a alpha squared plus b alpha plus c equals 0. If we plug beta in for x in our characteristic equation, we're going to get a beta squared plus b beta plus c equals 0. So we're assuming a solution of this form here. So now we know how to find out what alpha and beta are, what those numbers are. We basically take our difference equation, and as I've already said, we write down what's called our characteristic equation, which is a quadratic equation, and we solve this for x. And if we solve this, as we've seen, we'll get x equals alpha or x equals beta. And then we can write down our solution to the difference equation. We'll have some arbitrary value p times alpha, which is one of the roots of the characteristic equation to the power of n is the variable, plus another arbitrary constant q times our second root beta to the power of n.